Well, good morning. So, please bear with me, I'm still kind of new at this. But anyway, I'm just checking over here because I've got, hopefully, the actual live video playing on this other computer over here. Hopefully. I don't know. I'm not sure if it's actually playing. Okay. All right. All right. So we're good. Hi. Welcome to the party. This is my second official Ribbit Nerding live stream, and my name is Paul, and so what I'm hoping to do today is assemble an RC2014 mini kit. And let me just see if I can make sense of things. I have many things going on. Okay, so let me just do that, and then do that, and that. Okay, so this is the assembly guide. If you go to if you go to rc2014.co.uk, you can find your way to the assembly guide if you want to follow along with all the excitement. But this is the sort of thing that we're going to be doing. Now, a little bit of background. The RC2014, as the name suggests, was originally designed as a project for a retro computing fair, and so let me just make sure. Yeah, okay, so looks like I've got audio. So the oh oh dear. I'm gonna minimize this so you guys don't have to watch that in the background. Yeah, so the RC2014 was originally designed for a retro computing fair in 2014, as I understand it, and it's a Z80 based computer that basically leverages vintage components. So while it doesn't use like the little 1K bit ROM chips or anything like that, you know, it uses modern RAM chips and modern EEPROM chips and stuff like that. But like all the glue logic is 7400 series or 7400 HC. It's a Z80 based machine. You know, it's very, very simple and straightforward. And the original design of the thing basically just had BASIC as the programming language, as the operating system, quote unquote, and that was it. But there's been this whole ecosystem that's grown up around it, and one of the things that people have done is built disk controllers and, you know, a standardized way to implement CPM, which was Gary Kildall's original PC operating system, which was patterned after a mainframe operating system. I can't remember which one. It might have been, I don't know. Anyway, it's not relevant. CPM was the original, like, consumer small computer operating system, microcomputer operating system, as CPM a control program for microcomputers. That's what that stands for. So CPM was basically the de facto operating system for Z80 based computers and 8080 based computers until the IBM PC and MS-DOS came along. Well, there was a period of transition there, but after a few years, CPM kind of faded from the scene. So anyway, people came up with these modules that you could plug in. The original RC2014 was basically a backplane board that had a bunch of 40-pin 0.1-inch space header type slots. And so there was a CPU board and a ROM board and a RAM board and a clock board and all these kinds of things. And the idea there was to make it so that it was very maker friendly. If you decided that you wanted to do some other kind of crazy thing for I/O, you could do a crazy thing where you could pull out the original RC2014 I/O module and put in whatever you want. And that was great. And so that facilitated the CPM implementation on the RC2014. So the guy who originally created the RC2014, which you can buy on tindie.com, TINDIE.com. The guy who created the original RC2014 recognized that the design of the RC2014 was great from a modularity standpoint, but it kind of stunk from a standpoint of how much soldering you had to do, because for every one of those slots there's a socket with 40 pins on it, and then there's the pins on the card edge that you also have to solder on. And so to set up the backplane board, you've got, I don't remember if it was 8 or 10 on the whole, I can't remember what the kit name was, but there was like a smaller version of the backplane that only had 5 slots, and then there was like the minimum number of slots to accommodate all the modules that came with the kit. And then there was a larger backplane that had 8 or 10 slots on it, and so to fully populate that, you've got to do 40 times 8 or 10 slots worth of sockets, and then of course for each board you're putting in there's another 40, and then there's whatever components are on the board. And the modularity also made it so that you may have to duplicate some glue logic or other functionality on multiple modules, just to be able to accommodate like different I/O or things of that nature. So long story short, too late. So that's basically what the RC2014 was. The kit I'm doing today is the RC2014 Mini, which consolidates essentially all of the functionality of the original RC2014 kit into one printed circuit board. Ta-da! Which is great. It's a very compact version of the RC2014. Now, the other kit that I'm going to build, probably not today, but I have it, is the Cpm module, which just stacks on top of this one and gives you a compact flash card and a disk controller and whatever glue logic is necessary to run CPM on the RC2014. And I believe there's a separate ROM chip. I think the ROM that's on here goes away, and the ROM that's on the the CPM board is the one that ends up being used. So anyway, this is the board for the kit. I have, because of all the COVID craziness, I'm sorry, human malware. I shouldn't be saying the word COVID, I guess. This video will probably end up getting flagged. The human malware thing that's going around, and because of all the excitement over the UK variant thereof, I've already taken the liberty of unboxing everything and spraying everything down with, you know, anti-alcohol, and splitting the parts out into containers and such. So what I'm going to do is I'm going to switch cameras, and we're going to go through a little parts inventory. And but before that, I want to show you something. Let's see, where is it? It is there. And if I do, oh god, this. So I don't know if you saw the picture that I posted a little while ago of the streaming rig and the bench, but I've got these 10-inch 1080p displays down here under this camera, and one of them is the second display for the computer that I'm using to show you things, and so unless I'm actually looking at that display, I can't make any sense of what's on it. So let me show you something real quick. If you're doing these kinds of kits, I recommend what's up on the screen now. These are little, they call them souffle cups, and I don't get it. But because I mean, they're plastic. If you put them in the oven to bake a souffle in them, you're done. But let me go to camera 2 here for a second. So here we go. So this is an example of the plastic souffle cup, and in here I have a couple of capacitors, and this is just a great way to keep your parts segregated and not accidentally dump them on the floor. As you can see here, the cups are very cheap. I mean, 200 sets for $12, and for most components they work really well. I mean, for ICs, for example, these are the all the ICs that go on the RC2014 Mini, and for these, no, the souffle cups are just too small, and these should by rights be on anti-static foam anyway. So the souffle cups are not great for that, but for things like jumpers and tactile switches and power jacks and what have you, they're fantastic. And again, they're cheap, they're reusable, and I strongly recommend. So let's go through what parts we have. Here's another little bit of information. So if you're going to order the RC2014 Mini kit, there's two options as of right now. There are two options that you can select. One is to get an FTDI adapter. So this allows you to use a USB micro connector on one side, and it gives you basically the ability to use the USB as a serial console. So it plugs into a standard serial connector, TXRX, power and ground, and I think clock, clear to send. Yeah, clear to send, ready to send, TXRX, 5 volts and ground. And basically that allows you to interact with the computer. If you don't already have an FTDI cable around, just get the little adapter board. It's a bargain. Get it with the kit, save you some grief. The other thing is originally the RC2014 was only you could only use it with a serial console, right? But and I don't know if this was originally done by the guy who who did the original RC2014 design, or if this thing was originally implemented by somebody else and he released it as an official RC2014 product. But there's a way to use a Raspberry Pi, as a terminal, right? So that you have the ability to do keyboard in and video out without an extra computer hanging off the side. So again, there's an option on the RC2014 mini kit where you can get the Raspberry HDMI mini to HDMI adapter and the necessary headers and related accoutrement to attach a Raspberry Pi to this board. It also comes with the SD card, which I believe already has the image that's appropriate to use the Raspberry Pi Zero as the terminal. So, but for today's build, I'm going to hold off on the Raspberry Pi part. So I've bought the Raspberry Pi option for the kit, but I'm not going to be installing the Raspberry Pi portion as of today. The other thing I'm not going to be doing today is, so let's look at this. So move this way a little bit. There we go. Okay, so here along this edge of the board is the traditional RC2014 bus connector, and there's two different ways that you can do this. You can do it as a straight pin header or as a right angle pin header, and I'm going to hold off on this because I'm pretty sure I don't need it for basic operation of the core RC2014 mini kit. And the other reason is that because the CPM board is going to go on top, I want to make sure that the pins that go in here align with that board so that the standoffs align correctly. And so the easiest way to achieve that is to basically assemble the sockets on the other board and the pins on this board, sandwich the boards together, line up the standoffs, and then solder it. So yeah, those are the caveats for today's build. So at a minimum, we should be able to boot this up into BASIC and see it work. So that's the plan. So before we get too carried away here, I do have a video that I want to show you, which is just a little tour of the bench and the streaming rig. And this is in part to give me a second to get things organized. So let me is this playing? Play. Okay, so let's do this, and I'll see you in a bit. Here's a quick tour of the electronics bench and streaming rig. So this is an old 2008 iMac, which now runs Linux because Apple doesn't support it anymore. This is a Rigol 4-channel oscilloscope. This is my Dave Jones Special EEV blog multimeter. This is camera 1. It's an old Canon that I had bought while doing NewsUndies. SM58 Shure microphone. This is my solder / heat gun rework station, which is a new acquisition.
pan of ice for PCBs, another camera, and this is my magnifying lamp. Ta-da! Everybody should have one. And then over here to the streaming side of things. So this is the ATEM Mini Pro that I use for video switching and streaming output, and the display for it. This is the audio mixer. This is a Alesis Mini Mix 8, a USB Mini Mix 8. Raspberry Pi 400, which I use both for checking things out on content that I want to look at, and prepare stuff to be put over here on the ATEM. So like title cards and stuff like that, I don't have to go through the control software on the for the ATEM in order to get new pictures available. That's just camera 4. The second display on the Pi 400 is camera 4 on the ATEM. And then this is, this is the Mac Mini that I use to connect to the ATEM and run the control stuff on it. So the Raspberry Pi 400 has two displays, two display outputs. One is just a regular desktop, and the other one goes over to the ATEM. And so anything I want to put up there, whether it's file browsing or code or anything else, I just slide it over to the second display, and the viewers can see it. And that is pretty much it. That's the whole deal. Now, obviously, from that camera view and that camera view, what you're going to see during the streams is going to be pretty limited, but that's the bench and streaming rig.
Well, wasn't that fun? All right, so excrement. There should be. Let me do that. Okay, so there should be tape. Okay, so blue tape. Everybody has different ways of doing these things. Some people use what they call blue tack, which is kind of a rubbery adhesive goo, almost like a silly putty or something. I've seen more references to blue tack in like UK. You know, retro computer people and all that kind of stuff, when they're doing repairs, they refer to blue tack. I haven't seen it so much here in the US, but in any event, it's a thing. And basically the idea is when you're doing assembly of things that could fall out of the board, you can use blue tack or some other kind of temporary adhesive thing to keep the component stuck to the board. More often than not, I use blue tape, just blue painter's tape. It's reusable, and you know, at least for the life of a kit build or something like that, it works pretty good, and it doesn't leave any residue behind or anything like that. So we're gonna take a look at the, well, unfortunately there's a limit to how many different things I can have on screen at one time. So I've got the assembly guide up on the computer over here, and So if you want to follow along, you can bring it up. But the general idea, and let me do that and that. Okay, so hi. Of course, this is a little awkward because whenever I have to see whether something's in frame or whatever, I have to look over there. So I'm not ignoring you. But basically, this is the bag for the board, and I have a knife right here. So I'm going to liberate these things. This is the first time that I'm letting these things out. So, and I did, I don't know if it's Grant. I don't know off the top of my head the name of the guy who does the RC2014 kit, and I feel bad about that, and I'm sorry, because I really appreciate his work. But one thing that I did notice when I got the kit was there was a bag, this bag, that had the small components that I've put in the souffle cups in it, and apparently the seal didn't take quite right, I guess, and it leaked. And I think I have all the parts, and if I don't, whatever escaped, I think I might be able to replace from my own on-hand inventory. So I'm not terribly worried about it. So here's some decoupling caps that are going to go around the ICs on here. This is a right angle header for this 40 pin. We're not going to be installing that right now. I think this actually gets broken up to make, I'm not sure. I'm going to have to check the assembly guide. But these are all going to go off to the side for now because, as I said before, I'm going to be doing the CPM kit, and that's going to attach to this 40 pin connector on the edge here. Ta-da! So one of the cool things for the RC2014 mini kit is this little contraption, right? So IC sockets, these are the sockets for all the ICs that are going to go on here. And do I have audio? I have audio. Good. Okay, so the RC2014, the IC sockets are the first thing to go on according to the assembly guide. But this as a carrier for the IC sockets, I think is a brilliant, inexpensive solution. So I'm guessing that this is laser cut, but I don't know. But in any event, he's got the smaller sockets stuffed into the middle of the bigger sockets, which is a great space savings. I have my pokey thing here. So hopefully I can get this out of here without bending any of the pins. But these IC sockets, these are dual wipe, which is good. You can tell dual wipe because there's metal on this side. Let's see if we can focus AVE style. So there's metal on this side of the IC pin, and there's metal on this side of the IC pin. So you're getting, if this is the pin of the integrated circuit, you're getting contact on both sides, right? So that's dual wipe, which you want. There are cheaper IC sockets that are single wipe. They're bad. Avoid them if you can. There are also more expensive sockets called machine sockets, and they are nice, but they're quite expensive. And if you're doing anything in bulk, especially like prototyping, you might want to skip the machine sockets. Like for my Ribbit 65 computer project, I've been using dual wipe sockets, and I've gotten acceptable performance out of them, but they're not breaking the bank. So, you know, when I arrive at a final design for the R65, well, then I may go ahead and switch to the machine sockets. Now, important thing to note here. There's a correct orientation for the sockets and the ICs. Now, I don't know if we can get a focus on this, but yeah, okay. So there's a notch right there. Right there, okay? Each one of these sockets has a similar notch, and that indicates the end of the IC that is pin 1. Now, I'm going to double check on the build guide because, yeah, okay. So, the way this is laid out, all right, so here and here and here and here and here and here and there are the designators, the IDs for the individual ICs that go in here. So this one is, oh my god, I need glasses. I'm so old I can't see. So this is U4, U3, U6, U2, U7, U1, and U5. So the location of the identifier is where the notch is supposed to go, and that is evident in the build guide. So what I'm going to do is I'm going to go ahead and drop the sockets on here and get this in shot. There we go. So these, so again, the notch is here, the designator is at the same orientation. So by rights, these should just drop in without any difficulty. These are both 28 pin, I think. Ought to be, maybe. Or 24. Yeah, those are the right size. Scooby-Doo-wah. All right. So, it is my intention to practice proper ESD safe. I bumped my head on the camera because I'm terrible. It is fully my intention to practice proper ESD safety stuff here. I've got my wrist strap on, but I'm not hooked up because I'm not handling the ICs outside of the anti-static foam. So we're in good shape here, I think. So all right, so all the IC sockets are in place, and there's a couple of different ways that people might attack this. What I'm going to do to ensure that nothing untoward happens is I'm just going to put a strip of tape on here like this, and just make sure that that's all reasonably tight, and then do the same thing over here. Reasonably tight, such that when I flip this board over to solder these things in place, they stay. That is the goal. So I'm just gonna tear this excess tape off here, put it on my pan of ice for reuse later. Now this is not gonna give me perfect penetration in the through holes. In other words, ideally you want the sockets seated all the way down to the board, and sometimes you have to give them a little help to get them there. So, look, here we go. Ta-da! All right, so thing to do here is start soldering. Now, I am hoping that I can introduce a little more light here without introducing a whole bunch of glare, and that is not possible. Well, maybe I can. How about that? It seems minimally glary, and yet I can see things. Seeing things is important. Okay. So, we've got an IC socket on the other side here, an IC socket on the other side here, an IC socket here, 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 and here. Right? Now, the heights of the IC sockets relative to the board can vary a little bit, especially between like a 40 pin and a 14 pin. So relying on pressing the board down doesn't necessarily get you all the way to a perfect body of the socket resting against the board. So my solution to that is I'm going to do one corner on each socket, then I'm going to lift the board up and press the socket against the board with my finger and reflow that joint that I just did. And hopefully, historically, that's worked pretty well for me. So my iron is sleeping. Of course it is. It's coming back up to temp. Let's see. So this is the first time I've actually used this iron. It's pretty. The manufacturer, or the brand, quote unquote brand name, is Yihua, Yihua, and as AVE might call it, it's Chinesium. But it seems pretty good. The pencil is comfortable. Seems to come up to temp quick. The lead is long enough, but not too long. It's got a plug connector to go into the main box, which is nice. And the station also has, I mean, hopefully you saw in the video that I just played, the station also has a SMD hot air rework tool as well, and it came with a bunch of different tips for restricting the size of the airflow and all that. It seems like a pretty good piece of kit, and it wasn't terribly expensive. Got it on Amazon. All right, so let's start. Are we in frame? We're in frame. All right, so I'm just give that a little kiss of solder and let it cool, seize up. All right, give that a little bit of a push and reflow. All right, so that is the socket for the CPU. Now I'm going to do the opposite corner. And then I'm going to give it a press and a reflow. And that seems to have worked just fine. So now I'm going to do the same thing for the rest of these. Let me see if I can bump in the zoom a little bit. In fact, let me bump in the zoom a lot bit and then back the camera off a little, because it's like right where my head wants to be. Let's see. back the zoom off a little bit. All right, it's workable. I can live with that, and I won't bump my head on the camera quite as much, which is great. All right, so I want to be able to improve your view of what's going on and my ability to make what's going on go on. All right, so another corner. Give it a push. Give it a melt. Lovely. Ow. Yeah. The soldering iron is running at 300 C, which is 570 degrees Fahrenheit, and it's warm, I guess is a good way to call it. So yeah, it's doo-doo, doo-doo. Okay. Let it cool. Give it a push. You're doing the French mistake. Voila. All right. Okay. Give that a little goose. Ah, see, that one shifted. All right. And also, just as a kind of a side comment, you may hear what sounds like fan noise in the background. I have done what I can to try to mitigate that, both through expansion / noise gating and compression on the microphone. Well, primarily through that. But if you do hear fan noise in the background, that is in fact my server rack, which is, I don't know, 10-15 feet away. And I'm not turning it off. So I apologize if fan noise is annoying. And unfortunately, as John Cleese once said, we're stuck with it. So let's see. Yeah, this level of zoom is very confining. All right. So I don't know whether anybody's commenting on this, because as things are situated right now, I can't see Facebook. So if you are commenting and shouting at me because I don't know how to solder or whatever, thanks. But right at the moment, I can't see. Although, let me see if I can rejigger things, because might not be bad to take a moment to look. All right. So we're live, and the video is playing, but it doesn't look like anybody's commented, which is fine. I don't want to ignore anyone, is basically what it boils down to. All right, so the good news is that we've got the four corners done. on all of these IC sockets. So now what I'm going to do is peel the tape and double check to make sure that everything is seated as far down as it will go. And it's... oh, crap in a hat. I did not do all of the IC sockets. Ah, well then, let's do this one on the end. Let's see, where are we? Okay, so a little bit of love there. Oh, dearie me. Thank you for playing, rubber thing. And then bottom corner. All right. All right. So it looks like we're in pretty good shape. There's really not much in the way of an air gap between the sockets and the board. A little bit. But that may just be the plastic of the socket itself. Yeah. Yeah, I think we're in good shape there. So what I'm going to do now is I'm just going to go through and quickly solder all these doodads together. Well, not together, but hopefully not together. Yeah, there ought to be some kind of gap from one pin to the next. You don't want to short out between the pins. Alright, and give a little bit more love to this one. Alright. And we want to avoid cold solder joints. So there's a couple of different ways that you can approach soldering components like these, through-hole components. So with the through-hole soldering, you've got a pin that's poking through a hole in the board that has a pad on it. So one of the things that you can do is you can apply the soldering iron to the pin first and then apply it to the pad, or you can do the pad first and then apply it to the pin. As far as like people giving advice about soldering is concerned, I've definitely heard both sides, and I guess in part it depends on like what's the most delicate thing, because repeated thermal stresses on the pads can cause them to delaminate from the board, which is not what you want in most circumstances. But if you have a component that you're soldering that is particularly sensitive to heat, you don't want to linger too long on the lead of the component because you don't want to damage the component. So what do? Well, for fresh assembly, that is to say, in a situation like this where I am working with a brand new board and brand new components, my approach is to say, all right, let's just heat both things up at the same time, and let's try to get the solder to flow as quickly as possible, and get both sides of the joint wetted at the same time, because if you're wetting one side and not the other, then you're going to have a cold joint, and you don't want that. Well, most sensible people who are soldering things with the intention of having them work don't want that. If you're some kind of industrial saboteur, well, that might be a different story. But I mean, provided for the moment that the components that you're soldering in are not going to readily dissipate all the heat that you're putting in, then there's you're okay touching the board first. If you are in a situation where the component you're soldering is just going to soak all the heat, then yeah, you should preheat that and then touch the pad. But for things like these IC sockets, you really don't want to heat them too long, because then the body of the socket might melt, and that might cause the contact to not rest properly against the pin of the IC that you're putting into it. So, you want to move quickly if you can. And similarly, you don't want to linger too long on the pad, because there isn't much pad. I mean, I don't know if you can really make out. Yeah, the actual donut of tinned copper on here is pretty small, so you don't want to linger on there very long. You want to linger long enough to melt the tinning, the solder that's already on the pad. You want to linger long enough to heat up the pin that you're trying to solder in place, and to have the solder flow between the two so that they're both wetted. But not substantially longer than that. So, I mean, the wetting process depends on all parties involved being at the melting temperature of the solder. So, if you're in a situation where you've got one part of the mixture is hot and the other part of the mixture is cold, that's not going to do you any good. But for most of these electronic components, resistors, capacitors, things of that nature, you're pretty much in a situation where the pin that you're trying to solder isn't substantially more of a heat sink than the board. And so in that setting, I don't really see much of a need to bias toward one or the other. Now, when you're talking about things like power transistors that might have a heat sink attached to them, and you have to solder the heat sink to the board, well, yeah, try to heat the pin first. Or sometimes for surface mount components, like for instance power transistors sometimes, or power rectifiers or whatever, will have a tab on them that you're supposed to solder to the board. Well, again, you're talking about quite a bit of additional thermal mass there, so imparting the necessary heat to the component first is good, because you don't get in a situation where you're going to damage the adhesive that's keeping the pad on the board. One other thing to try to keep in mind is when you're soldering, particularly like these dual wipe sockets, the pins are flat, right? So they have one axis in which they're long and one axis in which they're short. And so if you approach like this pin that I'm about to solder from the side, it will have a tendency to want to bend. The problem with that is the pin has a spring component to it, right? So it's if you bend it a little, if you bend it a little, it will want to spring back. And the difficulty with that is that you've applied your iron, you've moved the pin a little bit, you've soldered, you've pulled your solder away, you've pulled your iron away, and now that pin is going to move in the pool of still molten solder, in the pool of crystallizing solder, right? Which is bad, because then what happens is you end up with this situation where the pin is moving away from where the solder is cooling, and you don't have electrical contact. And it's more difficult in that situation to identify a bad joint visually, which is a pain in the neck. So the next thing I'm going to do here, and I wonder if we can get this on camera, because this might be interesting, or it might not. Let's find out. So what I've got here, oh cool, neato. All right. I didn't mean to blow your head off. Okay, so can we see things here? Oh, this is terrible. All right. So I am going to try to do a quick visual inspection on these joints to make sure that everything is properly wetted. And if not, I'll give some things a reflow. But unfortunately, what you can see there is hot garbage. So I apologize for that. Okay. So as far as the big sockets go, I think we're in business. I just have to do the little sockets next, because as before, I neglected them, and I'm sorry. Yes, you see? The little souffle cups just saved my neck. Hurrah. Very much worth the few dollars that I spent on them. Alright, so we are in shot here, and so these three 14-pin 7400 series IC sockets are next on the agenda. So now another little handy bit of stuff with regard to soldering is to help ensure that the components that you're trying to solder together, in this case the through-hole pad and the pin of the IC socket, are at the appropriate temperature to be wetted. Don't apply your solder to the iron. Okay? You've got the iron, you've got the solder, and then you've got the components. What you want to do in almost every conceivable circumstance is heat the components and then apply the solder to the components, particularly in the vicinity of where they're going to be joined. Now, I don't know, because I can't watch two things at once. I don't know whether it's clear from the camera whether I'm... Oh, I should address this glare issue. Sorry about that. Whether it's clear, but I'm approaching the pin from this side, and I'm applying the solder from this side. So what's happening there is it's the pin that's melting the solder, not the iron. It's the pin and the pad that's melting the solder. So people who don't have much experience with soldering might be inclined to say, oh, well, I'll just put solder on the iron and then put the iron on the thing. And that doesn't help you very much. Now, it is beneficial to have a properly tinned iron. That is, the tip of your iron has some solder on it, just to help with heat conduction from the iron to the components. But the real trick is you want the components to be hot enough to melt the solder. And you do that by applying the iron. All right, we're in the home stretch here, kids. Now, once I get these done, I hope you don't mind, but I am going to take a little break. I have to go and use the potty and attend to a couple of quick things, and then I will be back. So I'm going to put up a graphic. I would say, what time is it now? 9 o'clock. Okay, so I would say that no more than 15 minutes. So if you need to use the potty, grab a snack, whatever you want to do, this would be a great time to do it. Let's see. All right. So it's not pretty. I have to do flux removal, but all the joints look pretty not too bad. And I'm going to hold off on doing flux until everything is soldered down. But for the time being, at least, let me back the zoom off just a little bit. So for the time being, at least, this is where we are. I am going to step away for a couple of minutes. I would say I should be back no later than 9:20, probably a little before, but I'll try not to do anything terribly exciting between now and 9:20. So hang in there. Please be patient. And I'll be back shortly. Take it easy. All right. So we got a couple of minutes before the official return time. But for those of you just tuning in, I'm doing assembly of the RC2014 mini kit, and the IC sockets have been soldered in, all of the pins. So there's actually not a whole lot left to build here. Let me bring up camera 2 and picture in picture. Okay, so I'm going to take a second to look at the build guide, and because one of the things that here we go. Just trying to get it centered in frame. So the different components that are going to go on this board have different heights off of the board. And so one of the things that is recommended is to assemble a board like this, putting the shortest components on first and then building up off the board. And while you can do this by eyeball, or putting the components side by side, there's a bunch of different ways that you can approach this. The assembly guide for the RC2014 is nice enough to provide us with an actual build order, like put this component in first, then put this component in, which is handy. So according to the build guide, the next thing to go is the crystal, which is in here. It doesn't want to go to the center of the thing. There it is. So the crystal is the next thing we're gonna put in, and an interesting note from RC2014 guy. You know what? I'm just gonna Wikipedia and make sure because I really appreciate all of his effort, and RC2014. How about RC-2014? Huh. All right. How about rc2014.co.uk? Yeah, so contact me. Let's see what that says. Oh, golly. All right. So, the guy's name is not on the site, apparently. So, yeah, that's exciting. So anyway, yeah, so the crystal is the next thing to go on, and the crystal this is the silk screen on this is fantastic. So the crystal goes here, and one thing that he says is to allow a little space between the bottom of the crystal and the board so that nothing shorts out. And I'm looking around in front of me to see if I can find something that I can use as a spacer. I don't want to use tape if I can avoid it. Actually, you know what might work is maybe some of this cardboard. Yeah. Heck darn crud. Yeah, I don't have anything really great for this purpose. I have a guitar pick. Maybe that'll work. So, as you might be able to see here, that just sits right on the board, which is suboptimal. But if I put that in there like that, and then, but it wants to wobble. I want it to be as flat as can be reasonably achieved. Oh, maybe that'll work. Okay, so this is just a wooden shim, a piece of a wooden shim that just might do the job. So what I'm going to do is cut. Well, let's put this on here to get an idea of how wide this ought to be, because it doesn't need to be huge. So we'll just kind of split that a little bit like that. And let's see, kind of go where the split is. That works. And then give that a little bit of a chop right about there. Break that off. All right. So now we have a little bit of a spacer. Now, you might be thinking, gee, Paul, you just said that the components should be resting hard up against the board. Well, I did, but I was talking about the IC sockets. And the thing about the IC sockets and other connectors is, which end is the thick end? Because I don't want that stuck under there. I want to be able to pull this out afterwards. The IC sockets are actually connectors. And the difficulty is that when you go to insert the IC or pull the IC out, you don't want to be putting any extra stress on the solder pads if you can avoid it. Now, in a perfect world, you will only be inserting an IC once, and therefore the bulk of the stress will be on the insert. And so if you don't have the plastic body of the socket hard up against the board, what then happens is you go to insert the IC, the pins produce a lifting force against those pads and can pull them off the board. And that is what we regard as bad. So we want to skip that if we can help it. In this case, this crystal is not going to be repeatedly inserted and removed. And of course, there's the matter of the possibility of shorting out. So, all things considered, the best thing that we can do is follow the assembly instructions and not put the body of the crystal hard down onto the board. So I'm going to put a little bit of solder on here just to help with conduction, and solder, solder, ta-da. Now, we've got legs sticking up here, so we want to minimize the interference of those legs with the rest of our activity, so we'll just trim those off. And ideally, you want to not trim them on the solder. So I don't know if you can make that out or not, but the camera doesn't want to cooperate, I guess. But you want to not apply so much solder that there's a giant ball there. You want to there, our little shim is out, and as you can see, there's a little bit of a gap there between the doodad and the other thing. The doodad and the other thing. Yeah. Okay, so the next thing is the 6 100 nanofarad capacitors go where indicated, and that graphic I showed you previously indicates where they go. So the 6 nanofarad filter caps, so there's one that goes there, one that goes there, one that goes there, one that goes there. I think I'll have to double check. One there, one there. All right. Well, I'll just scroll down in the build guide. And whoops. Huh. Good job. So there. Ah, there. That's it. Okay. So these are capacitors that are on tape, which is intended to be used with pick and place machines, which is fine if you can make it out. But yeah, so this part is on top, and this is the backing. This part, the backing, is more rigid than this adhesive tape here. So there's a couple of different ways that you can approach this. If you're interested in minimizing the stress on the leads, you can try and separate the adhesive tape from the hard, stiff backing, and then just peel it apart like that. But in this case, it seems as though that tape is more adhesive than I was expecting. So we can just do that. And so that's what we're going to do. Ta-da! Now, with any luck, there's not a whole lot of the backing material behind the leads, and so we can just peel it off like that. Now, these capacitors are not polarized, so the orientation of them in the hole, whether this way or that way, doesn't matter. I don't recall if there are any electrolytic capacitors on this board. I don't think there are. So we don't have to worry too much about that. Let's see, where's the... Oh my god. Are my eyes that bad? Okay. So what I'm going to do is one side of this cap has printing on it, and one side of it doesn't. And so what I'm going to do is I'm going to orient these so that the printing is legible like for instance, this cap here, you can either orient it with the printing facing that way or the printing facing that way. I'm going to orient it so the printing is facing that way, so that if I or some poor schmuck at some point down the road needs to replace this capacitor, they stand a chance. I mean, for crying out loud, the printing on it is... I can't make it out. But if one had a handheld USB microscope or something, maybe they could. Now, notice that these leads are now sticking out of the bottom. With something like this, a capacitor or a resistor or a diode or something like that, you could, if you were so inclined, do the little tape trick on the back. But what I do is I just bend the leads out a little bit, just splay them a little bit, and that will keep them in the hole, right? So maximize your seeability there. There it is. Okay. So just splay the legs out a little bit like that, and that will help to keep them in the holes. So that's one. We got another one here, and we'll double check which side the printing is on, that side. So we'll give that a little trip in there, and we'll give that a little bit of a splay, like that, and carry on like you do. Okay, so having the printing oriented so somebody could actually read it isn't going to do us a whole lot of good with the one that goes in here, which is sad, but you know, you do your best. So we'll just disappear that little baby right into the crack there and splay those legs out. And let's see, so we got one there, there's another one that goes there, and the printing is on that side, so we'll turn it around. And I apologize if I'm out of shot. Yeah. Splay those little babies out. And where's next? There's next. And the writing is on that side. So we'll do that. And as far as ESD goes, these are passive components. They are not static sensitive, so I still don't have my wrist strap on, and that's okay. And one goes here. Okay, so we got those in. Now we should have two 22 picofarad caps, which should be these. Again, with the little cups. And we're just going to solder all these capacitors at the same time, just to save a little grief. And so we'll peel these off the tape. Now, as far as reading the values on these caps goes, typically they're a 3-digit code. The first 2 digits are the first and second significant digits in scientific notation, and the third digit is the exponent. Now with capacitors, I'm not entirely sure. Let me get the mag light here. Freaking doodad. Oh my god, my eyes are shut. 22J. Alright, so yeah, I don't know. I'm gonna have to double check on that. But the 22 is 22 Twain House. Let's see. Okay. You know what? I've got this fucking bounce panel that I should probably get, and that would help things out a lot. So anyway, the J probably corresponds to
the picofarad type designation. So, but the 2 are the two significant digits that are in the value. And that's a pretty common thing for, run-of-the-mill components. The values are stated in 2 significant digits and a scientific notation exponent part. Now, resistors are entertaining because, by virtue of the fact that they're cylindrical in shape, and there's no the leads come out axially on most small wattage resistors, so the orientation of the component on the board makes it difficult to reliably print numbers on there. So what they do is they use color coding, where there's stripes around the cylinder, and if you're holding a thing in the proper orientation, then what you see is the first significant digit is one color stripe, the second significant digit is the next color stripe, the exponent is the third color stripe, and then there's a fourth color stripe that is the tolerance. So that's 5%, 10%, 20%, which specifies how close to the stated value the actual value is at time of manufacture. Of course, that can change over the life of the resistor depending on what kind of exciting things that you're exposing it to, but that's the deal there. So that is pretty much just on resistors. Caps usually have some kind of a printed letter number combination of things. Oh, come on, iron. Play along. Little blob. Just to get things started. Okay. So most of these caps that are on here are decoupling caps, the caps that I'm soldering right now. They're called decoupling caps, and the idea behind these caps is we're dealing with a bunch of digital logic circuits here. Now, the way digital logic typically works is you're basically just employing amplifiers, and so you're using a control voltage to control the output of an amplifier. The control voltage is in a normal amplifier, like an audio frequency or radio frequency amplifier, the control voltage is small compared to the output. However, in the case of digital logic, the source signal and the output signal should be approximately the same amplitude. Now, the impedance, which is active resistance, the impedance from the output of one stage of the circuit to the input of the next stage of the circuit should be high. That is to say, you're not drawing a bunch of current, but you are drawing some. And so what happens is, when you've got like a CPU or even a 7400 logic gate chip, 7404, 7408, whatever it is, there's so many amplification stages in there, and that what happens is when you switch states, the amount of current that you're drawing changes, and so the supply voltage changes. And so what you want to do is you want to stabilize the supply voltage on the you want to stabilize the supply voltage so that you're not transmitting noise onto the power bus. So the way you do that is with a little capacitor. And so the transients, the transitions from, you know, high to low, whatever your logic voltages are, the transitions from high to low, low to high, are isolated to the chip, and any dips in voltage or spikes in voltage can get taken up by the decoupling cap. So the decoupling cap is kind of like the suspension in your car for the power, the power bus on the board. So gonna go ahead. Oh, thank you, cord. I'm gonna go ahead and trim these leads. Is this the one that I was using? Yep. All right. I'm just trying to keep my place in some kind of order here. Whoa. Well, I'll get that later. That's fine. Now, back in the old days, when I was dumb, I would have laid these leads flat down onto the board. It's unnecessary, and it makes doing repairs later a real pain in the neck. So, you know, if at some point one of these decoupling caps fails and I need to pull it out, it's going to be much easier to do that. It should be solder mask. I don't know. You see right there on that decoupling cap that looks like there's a little bit of schmutz? You take a look at that under the magnifier and see what the heck's going on there. Just a sec. Okay. For a second there, I thought it was a bit of solder snot that might have impacted the solder mask. So, for the uninitiated, you see, let me just get rid of the glare. So you see on this board how there's blue everywhere except where the white is. The white is screen printing, so that's just ink that they screen print on, or paint. But the blue part is what's called solder mask. So when they make these boards, they build up the fiberglass, the layers of fiberglass. If you look in the edge here, there's 2 or more layers of fiberglass and epoxy, and I believe this is a 2-layer. This might be a 4-layer board. I don't know. I can't really tell, but yeah, this has got to be a 4-layer board. Yeah. So in any event, this when they build this board up, let's pretend this was a 2-layer board. There would be the fiberglass in the middle, and then on the top and bottom face of that fiberglass, they would lay a copper cladding, right? And that's adhered to the fiberglass or the epoxy. And then what they do is they lay photoresist on there. This is this coating that when exposed to light, it either does or does not resist etching.
They have an etchant chemical, and so they spread this photoresist on there. They have a film, like a negative of the traces that are supposed to go on the board. So they have the fiberglass board with the copper cladding and the photoresist, and then they put the film over it, and then they shine light on it. I believe it's ultraviolet. When they shine that ultraviolet light on there, the stuff that's exposed, and I believe the film is a positive, which would mean that the exposed portion of the photoresist will be degraded. Then they put that in a chemical bath, and it takes away the stuff that was exposed to the light. Then they put it in the etchant, and that takes away the copper that's not covered by the photoresist. Then they rinse it off, and you have the board. Why did I say that? Oh God. Yeah. So that's how these boards are made. So the blue, right? So once that etching process is done, then there's a next step, which is called solder mask, and you'll see on this board here, you see like all these little pads here show up as silver, and all the rest of it is blue, right? So what happens is, similar to the screen printing process, similar to the mask for the etching, they have a thing for the solder mask that exposes some of the copper cladding that's been formed by the etching process and covers the rest of it, such that you can't solder in any of the blue places here without etching that coating off. And so it gives you a little bit of insulation so that you're not just shorting things out randomly, and it protects you when you're doing the assembly, because it's harder to short between pins. Like these 40 pins are all very close together, and if there was no solder mask there, it would be very easy to bridge between them. It's still not impossible to bridge between them, but it's more difficult with the solder mask. So yeah, that's the solder mask, and that's why it's there, and it is our friend. So the reason I brought that up was the schmutz, right? Now I remember. So I couldn't tell, it was whitish in color, and I couldn't tell if it was a blob of solder that had like landed on the mask, or if it was some other little schmutz. If it was a blob of solder that landed on the mask and it was sufficiently hot, or there was a scratch in the mask or something like that, it's possible that the solder could have touched the underlying copper and shorted something or whatever. So I just wanted to make sure that was clear. Clear as in not a problem. Okay, so we've got all the caps in. Let's scroll back up here and see what's next. Fit the resistors where indicated. Okay, so the resistors. This is great. All right, now the resistors are also mounted on tape for use in a pick and place machine. Okay. So this stream, I'm planning on ending this stream at or around 11. I don't want to run any later than 11. So I'm just trying to keep an eye on the clock. That's all. All right, so where indicated. So this is the orientation of the board on the thingy. And use resistor offcuts for links. Okay. So, Scooby-Doo, let's start with, let's do these in the order that left to right as they appear on the build guide. So 1Ks, we got 3 1K resistors. Now, I don't know if you can make this out. Will you focus? You're not going to focus, are you? All right. So, I don't know if you can make this out or not. Let me do that. Oh yeah, that's visible. Okay. So, this is the correct orientation to read left to right for the stripes, right? So we've got a brown, a black, a red, and a gold. So brown is 1, black is 0, and red is 2. So you've got 1, 0, 0, 0, which is 1,000. That's 1K ohms. The gold, if I remember correctly, the gold is 5%. So the tolerance on these is 5%. We can double check it. I happen to have my handy dandy Dave Jones EEV blog multimeter here, which, if you're in the market for a multimeter, I recommend, because it works good and it's not terribly expensive. All right, so let's move a couple of things out of the way here, and let's see if we can actually get everything in shot here. All right, so there's the resistors, and I need all the hands. Select. Okay, so that's good. Let's do this not on the mat because the mat is conductive. .987K. So that is in the ballpark. That is within 5% of 1,000 ohms. So I will take that. Beautiful. So, let's get ourselves oriented again. There's the board. There's the board. There's our resistors. And so, we'll get one of these little babies in here. So these 3 resistors all take 1K. So, I don't know if you saw me bending the leads on here. There's only 500,000 different ways to bend the leads on these. You know, some people use pliers, some people don't. I tend not to, just because, you know, for these 1/4 watt or 1/8 watt resistors, these are 1/4 watt, I think. The leads are so thin that the stress that's going to be applied to the body of the resistor by just bending them with the fingers is negligible. Excuse me. Let's see. Okay, I'm going to go ahead and put this 4th 1K in place. That's supposed to go in R7, which is over here. Just splay the legs out a little bit. All right, So these two, R9 and R10, are supposed to be 22K. So that would be 22 or 2.2. Yeah, red, red, orange. So there's a red, red, orange. Oh boy, excuse me. Oh, no, I read that incorrectly. R10 is 22K. Haha. Alright, so yeah, I just grab the body of the resistor. Boom. I'm also trying to remember to orient these so that if you can read the label of the board left to right, you can read the color codes left to right. It just, again, if at some point some poor schmuck has to do any kind of troubleshooting on this, it's going to be easier on them if they can actually read the values of the resistors without jumping through any additional hoops. All right. And actually, one nice thing about the build guide is for each of the resistors, they have the color codes right there. So brown, black, orange, which is 10K. So brown, black, orange. That goes in R9, according to this. So we'll go ahead and stuff that. Display the legs. Let's see. So we already got the 1K. We got a 1 mega ohm, which is brown, black, green. Brown, black, green. I was just thinking about how, you know, this is apparently a 4-layer board, just given how few circuit traces there actually are on either side. And my Ribbit 65 board is a 2-layer board, and it was just freaking nightmare to route. All right, so that's the 1 meg. The next yes, you son of a bitch. 3.3K. All right, so orange, orange, red. There we go. So there's a bit in the build guide that well, I can show real quick. Hold on a second. Let me get it situated here so you can see. Here's a little caveat for you. Hold on. Here we are. Okay. So now you might be inclined to just read across the picture. Right? So you've got 22, 10K, 1 meg, 2.2, 2K2, 300R, and 3K3. But you'll notice that, in fact, the resistor, if you're going down that stack of resistors on the board, the one that's below the 1 mega ohm is actually a 3.3K. So yeah, if you get one of these kits and you're building it, proceed with caution, because that's definitely something that can screw you up. And here's another little wrinkle. Remember how I said typically the assembly guides for these things say to do the lowest components first? Well, if we were doing that, we would do these resistors first. But, you know, they're recommending this, and I'm not complaining, so no worries. Splay the legs out a little. Who's next? 2.2K, which is red, red, red. Okay, red, red, red. And orange, orange. That's curious. Oh, okay. So I showed you before that the things are not in the order that you might think. And that has swum up and attempted to bite me in the bottom, but I was actually doing it the right way. So, because the bottom one in that, the bottom one is 330 ohms, which is orange, orange, black, not orange, orange, red. So, doop. All right. So it looks like we're in business. Just check to see if there's any other. Oh, right. So in the build guide, you see in the magenta there where it says use resistor offcuts for links, and there's a thing that says link and a thing that says link and a thing that says link. So I'm going to go ahead and do that, but in order to have the resistor offcuts, I first have to solder the resistors in place. So let's get that done. Okay. So there's the board. Most of our resistors are in this area here, which is convenient. And I'm going to do this way across the board and trim the leads as I work across. So I'll do the first 3. Let those cool for a moment. Then trim the leads in one go. Do the next 3. Give it a moment to cool and trim. The leads. And of course, right next door are these other 2 that I didn't want to accidentally trim until they were soldered, so hence the caution that I was exercising there. And I don't want to accidentally melt and or short to, bridge to those other 3 pads, so hence the coming at it from weird angles business. Oh no! Come on. There we go. So what just happened is I didn't have a really good contact on the pad, and the solder, the pad was just hot enough to melt the tip of the solder, but not enough to get it to flow. And so, yeah, it ended up with it ended up sticking to the pad. And I hate it when that happens. Alright, so we'll take these two and set those aside for bridge use. And now we're in the home stretch for the resistors. This is pretty cool. Alright. Ah, come on, you. Like sticking the solder down into this forest of splayed legs. With the eyes being hot garbage. Do not recommend. All right. It's like those old aerobics videos in the 80s. You know, 3 more, 2 more, 1 more. I'm sure nobody remembers those. All right. So, go that way. Sloppy trimming. Take a little bit extra off of that. Man, this is a disaster area. Alright, that's good. Alright, so we've got we've got our resistors in place, and now we need to do our jumpers or bridges. So my plan is to just bend them around my little pick tool here, and then hopefully, do I have this upside down? I don't. Okay. Oh boy. All right. So this collection of links, actually, you know what? I am going to scroll up to the text of the thing. Oh God, come on. Okay. So we got the caps. And the links. Okay. So these links are oriented as you look at it on your screen, up and down, both of them.
Now, if I was smart, which I'm not, but if I was, I would probably be inclined to do these with jumpers and pin, oh god, and pin headers, rather than just soldering these lead clippings in here. But the lead clippings are certainly more secure, I will grant that, but in terms of being able to break these connections for some reason in the future if need be, that's more readily facilitated with jumpers than it is with these soldered links. Okay, put that in, splay the legs. How many more do we have here? These three. All right. All right, so I think we're approaching the home stretch here. As far as identifying weird components and putting them in and all that kind of stuff. I hope we are, anyway. And then with any luck, we'll take one more little break, and then wrap this up. And you may have noticed that I put a question mark on part 1, because I really wasn't sure how long this was going to take. And it's actually taking, I mean, I have an original RC2014 kit, and the amount of time that it took to solder that baby together was just, woo, that was something. That took a while. And this is going a lot faster than that. Okay. So, per the orientation of the thing. Oh, green LED. Hurrah! Let's get that installed too. I almost didn't even notice that. Is this the green? That's the green LED. Okay. Now, another thing we can learn about. Light emitting diodes, right? So this is tiny and it's not focusing and it's making me sad. But when you look at this thing edge on or end on, is it focusing? Maybe it is. This is a tiny LED, but here, there's a flat spot. There's a flange at the bottom of the LED, at the bottom of the body of the LED, and on here there's a flat spot where the flange doesn't appear. Correspondingly, there's a long lead and a short lead. I don't know if you can make that out. Long lead and short lead. Okay? The way I remember this is the short lead is minus and the long lead is plus. And if you take the plus and do that, it's longer than just the minus, right? So the minus is the cathode, is the short, okay? On the board, can we read that? Yeah, okay, so this is where the power LED goes, and you see there's a little tiny K right there. Trust me, you see it. So the short lead is the cathode, is the minus. So we'll just put that in like that. And we'll splay the legs. And so that step is ready to be concluded with actual soldering, which we will now do.
and we're gonna blast through this real quick. I'm gonna try to not do a bunch of talking because I really need to take a little break for a second. All right, so I'm just gonna solder up these links. Got the power LED. Come on. Come on. There you go. Link, 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 link. Link, 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 and power LED. Okay. All right. That's lovely. So we'll just trim these leads. Whoops. Those are not the trimmers. These are the trimmers. Trim, 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 dooba-dooba-doo, trim, trim, trim. And you may notice that when I trim these leads, I'm actually holding onto the lead before I give it the old chop. And the reason I'm doing that is, if you've never done this sort of thing before, it's possible for the trimmed piece of metal to just fly off into hyperspace. And that can be sad making because A, you may never find it again, and it could be problematic when you go to sit on it or run your hand across it and it stabs you or whatever. But also, funny third thing. No. I know there's well, so strictly speaking, these little things, if you're using lead solder, in which I am, you're going to be in a situation where there's going to be some solder residue on there, probably, and you know, it could end up in food, in your mouth, whatever, bad. You don't want lead. So all things considered, oh, and of course there's a possibility the thing could snap off and go in your eye, which, you know, 10 out of 10 would not recommend. So yeah, if you can, if you have enough room to actually grab it before you snip it, grab it before you snip it. It's the right thing to do, like oatmeal. So on that note, by my timepiece, it is 10:15 a.m. I'm going to step away for just a little bit, and then we will proceed and hopefully actually get first light here. Yeah, we're real close. There isn't a whole lot more to install here. So let's meet back here in let's call it 10:25, and see if we can push through the rest of this. So thanks for joining so far and sticking with it, and yeah, so we'll see you in a few. Thanks. Uh-oh. Mr. Clever Guy. Hello. All right, so let me just confirm. Yes. All right. Is that just hairs? Oh, golly. All right. So, we're nearly back. I said 10:25, so I'm gonna stick to that. I'm here, but I'm not gonna get cracking until 10:25. But yeah. So the next exciting thing is the little pin headers and the reset button, and those are jumpers. Let's see, got the power socket, reset button, and all the pin headers are cut, which is awesome. You set the jumpers back over here for now, and I guess while I'm here, I'll go to camera 1 and collect up all my trimmings, hopefully. Alright. Actually, those can go in there. Hurrah. Whoop. Come on, little buddy. That looks good. Hokadoke. So, by my clock, it looks like it's 10:25, plus or minus a few seconds. So, let's get cracking. Let's do P&P and do all the needfuls. Now, we'll go ahead and do the pins first. I don't want these things to go flying away. I'll put them over there. Alright, so a souffle cup with the pins, and I am hoping that these are all set up appropriately. Okay, so we're going to do the right angle ones first. According to the build guide, these two FTDI headers should be right angle. So I'm going to go ahead and put those in like that. And I'm gonna tape them with a piece of tape, like you do, and hopefully that's good enough. I'll turn that little baby over, and we got oh, that's unfortunate. Alright, I guess I'm gonna have to do that part by hand. I need 6 more hands. Crap. Maybe if I do that? No, that's garbage. Okay, well, I'm going to do 1 pin and then I'm going to do alignment. So I need glasses because I can't see. And we'll let the soldering iron come back up to temp because it was napping. 572, beautiful. Just blob the solder on there. Yeah. Come on, Flux. Do your thing. Alright, we'll go ahead and do that. So I recommend that you have something like this, if you don't already, in your kit building kit. because this is great for cleaning your solder tip. Because what happens is the flux core of your solder will burn and accumulate schmutz on the tip of your soldering iron. And what happens as a consequence of that is you don't get good heat conduction to your stuff. So periodically you need to like overload it with cleaning. And the way to do that is with flux. Now, I don't know if you can really see what's going on here. I apologize for the bad lighting, but I'm going to try to ensure that this thing is in all the way and straight, and not burn my freaking fingertips off. Okay, so that big right angle header is in and straight. So I'm going to go ahead and wrap this up. And the thermal mass of these header pins is greater than the leads on the little components, little passives and stuff. So a little more heating time is recommended. So next I'm going to do 1 pin of the 2-pin header, and I'm going to take the tape off, and that is messed up. So let's go ahead and do that. It's still not great. So the difficulty I'm running into is, I'll bend that with pliers, that's fine. Okay, so yeah, the difficulty I'm running into, let's see if I can show you. Can you see? Where is it? Where did it go? It's there. So one of the pins is sitting lower than the other. Actually, you know what? They look okay now. They're not perfect, but I think they're close enough. All right. And that's just a jumper goes there if you're going to be using FTDI for 5 volts. So, that's fine. Okay, so what's next? We have okay, so this 6-pin header would be for the quote-unquote universal keyboard. 3-pin straight header. So this is 2, 4, 6. That would go here if we were using the RC2014 universal keyboard, which we're not, but we got the socket, so might as well. 6-pin socket, yeah. Might as well use it. Okay. So that's here. And Scooby-Doo-wah. All right. So that's that. And one of the nice things about these headers and sockets and stuff is there's no lead trimming that has to go on. Okay, so the next thing is these doodads, and those are, I suspect, to be cut from here. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Yeah, because there doesn't appear to be any place else for these to go. Let me just double check on the build guide. Fit the 4 3-pin headers. Oh. Okay, all right, yeah. So 1, 2, 3, 4. Okay, so this should have 12 on it. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, good. So I don't know if you can see or not, but there's little depressions. Let me get this in the center, see if it'll focus. There's little depressions in between the pins. So what I'm going to do is I'm going to go ahead and cut these into 3-pin lengths with my little nippers. So there's 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3, like that. So one of these 3-pin duty bops goes up here, and I don't know if you can make this out, but there's a long side and a short side. So the long side goes above the board, like that. See the long side sticking up? So I'm just going to tape that and hope that it stays. And you want these, because these are going to be servicing jumpers, so you want these to stay more or less upright, but the exact uprightness isn't critical. 3-pin straight header. Okay. And then 3, oh, okay, I see what it is. 3-pin straight header. There's VCC and ground markings on these headers, on the silk screen for these headers, and it was just confusing me for a moment. So we'll go ahead and tape these headers down. And hopefully, oh my god, the tape is really not sticking the way I was hoping it would. Alright, well, hopefully the pressure of the board sitting on the bench will provide enough fizzy lifting drink to keep everything together. Alright, so I'll go ahead and hit this little baby. And then these 9 little babies. Oh boy, this is tight. All right, so before I proceed, these three pin headers each have one pin soldered. So I can remove the tape from the 3-pin that's up here, and I can remove this piece of tape, and I want to double check the alignment on these to make sure that everything is hunky-dory, and it appears to be, more or less, although that one could stand to bend that way a little bit. All right, good. So I'm just going to go ahead and solder the rest of these. Doopy-doo, where are we? There we are. Mine's shot, yep. Come on. Here we go. Come on. Here we go. There we go. Oh, come on. All right. All right, that looks pretty good. And what's next? Oh, yeah. The power jack and the reset switch. So what do we got on top here? We got the power jack. Now, we had talked about previously the matter of big pieces of metal and dissipating heat. So this is the power jack, and these are the lugs to solder onto the board, right? They're not huge, but they do have some thermal mass, and so there is some concern that you're not going to get enough solder. And you may also notice that these holes are enormous, so we're actually going to be filling these holes with solder because we want a good joint. Everybody wants a good joint. I'm just going to let that sit there for a minute. All right, so we'll go ahead and hit this one first. All right, we want to make sure that we have a good mechanical relationship with the board. Okay, so now I'm just gonna kind of tack the back end here a little bit. Come on. Here we go. Okay, so this is, there we are. This is tipped that way a little bit. So what I'm going to do is I'm going to apply some pressure, clamping pressure this way, while I reflow this joint, and hopefully I can get that to sit better. There we go. Let that cool, and then I'm going to hit this lug. And once I've done this lug, I'll reflow the back lug. So make sure we got some good solder on the tip so we can get good heat conduction between the two pieces, and then apply solder to the joint. Okay, and then one more time just to fill this one up. All right, so that's the power switch, and next thing is the reset switch, which is this. Just a little tactile switch, little right angle tactile switch, like that. Alright, so I don't know if you can see or not here, but there's narrowly spaced pins and widely spaced pins, and there are narrowly and widely spaced pins on the switch itself. I don't know if you can see, bending in ways humans should not bend, to try and show you, but we'll just go ahead and insert that like that. And again, now these tactile switches are nice because they've got a little hook in the pins, the back pins, that helps with keeping them in the hole. So what I'm going to do is I'm going to tack one of the back pins and then double check and make sure that everything is seated correctly. I said I'm going to tack one of the back pins. Okay. There we go. And make sure everything is seated correctly. And it appears to be. So I'm going to go ahead and solder the rest of these. Now the back pins are not switch contacts. Only the front pins are switch contacts on this switch. So, reset switch. Power LED, all the headers, all the sockets. What's left? Okay. So the only thing left are the 40-pin header here and the 40-pin header here. So this one is for the Raspberry, and this one is for the RC2014 bus, which, as I said, I'm going to pass on those for now because of plans. I can do a stream dealing with those in the near future. So the next thing is putting the jumpers on. So we'll go ahead and do that. Woo! So there's no soldering involved with the jumpers. Okay, so it says to put all three of these jumpers in the ground position for basic. So ground is that way. So there's, come on, sweetheart. There's one. There's two. There is three. And what else do we need? Okay. So if we're going to be using FTDI for power, do we want to do that? Let's pass on that for now. Set the keyboard jumper to Pi or Serial, depending on what keyboard you want to use. So let's do Serial for now, I think. Shrug. Do I have an extra jumper here? Oh, no. Oh, FTDI for power. Right. All right. So what I'm going to do with FTDI for power, so that's this 2-pin jumper here. This 2-pin jumper. So what I'm going to do is, so the jumper doesn't get lost, I'm just going to hang it off one of the pins, like such. So I don't know if you can see or not, but this pin is not connected by the jumper. Only this pin is. Right? So the jumper isn't jumping to anything, but it's still there. and hopefully won't get lost. All right. And that's the bill of materials and the schematic. First time use. Well, they didn't even tell us to put the chips in the sockets. At least not in the pictures. Let's see. To fit the ICs. Yeah, okay. So we still have 10 minutes. So we're going to go ahead and do the ICs. And this is where we're going to use the thingamabob that does the job. Now, there we go. Okay. So I am going to put my solder over here because we're done soldering. And I'm going to go ahead and say that's ground. Oh, is that a banana plug? It's a banana plug. Fucking A. That's awesome. Alright. So, let me just double check. I want to make sure. Make sure ground is ground. Because it's important. Is ground ground? Is ground ground? By rights. 1 mega. Perfect. So, you probably couldn't see what I did there. I'm fairly certain you couldn't see what I did there. I used the multimeter to my solder station also has a DC power supply in it. And so I wanted to confirm that, because I was going to plug my banana plug for my anti-static wrist strap into the ground on the power supply, and I wanted to confirm that ground there is ground and ground everywhere. So like the third pin on the power plug. So the first thing I did was my oscilloscope has a ground tab as well for testing. And so the first thing I did was I set the multimeter to volts, and it auto detects AC or DC. I set it to volts, and I did a connection between the ground pin on the power supply to the ground pin for the test lug on the oscope, and it was 0 volts. So then I switched to ohms, and I did ohms, and it was 0 ohms. So that suggests to me that, one, I will not be electrocuting myself by doing this, and two, I am now grounded, which means I'm theoretically ESD safe. So, good things. Alright, so here's the RC2014 Mini, and here are the ICs. Now, delightfully, the screen printing here says what all of these things should be even. To see it on camera, it's really tough, but even in here, it says what they're supposed to be. 74HCT32, 74HCT32, 74HCT04. So, the print on here is big enough that I can read them, which is great. So there's one little trick that Okay. We'll just go ahead and start. And I'll show you as I'm proceeding. All right. So I just used my little pick, my little right angle pick, to get under the chip and lift it out straight, as opposed to trying to pull it out this way, because then you could bend the pins, and you don't want to bend the pins if you can help it. However, oh, and this one's bent a little. Of course it is. All right. Now, I don't know if you can make this out, but oh god. These pins are splayed out a little bit, right? They're not parallel. And you want them to be, oh, this one's bent in as well. Not great. Now, oh golly, gee whiz. Okay. So, this will not fit perfectly in the socket as it is. There needs to be a little bit of help. Now, there's two ways that you can do this. One is, and I'm going to try this first. Okay. So remember I said about the notches before? You probably don't. So the notch, there's a notch on each of these chips, which you probably can't see, but it's right here. Yeah, you can kind of see it. Okay, that little notch corresponds to the notch here, which you also probably can't see, but the U2 marking on the board corresponds to the position of the notch. The notch here corresponds to the notch on the chip itself. It's important to get that orientation correct. You could kill a chip. Now, this is an MC68 B50. 68B50. Okay. Now the pins on this chip are splayed out a little bit. There's two ways you can mitigate that. One is to put one side of the chip in the socket and leave the other side out for a second. And I don't know how to do this so you can see it while I'm doing it. But like that. So the pins that I'm moving now are not in the socket. The other pins are, right? While keeping downward pressure on these pins and lifting the chip so that these pins clear the top edge of the socket, a little bit of lateral pressure here might, nope, it's not gonna. They're too far splayed out. So what I'm going to do is the plan B version, which is hold the chip like such, place it on the bench so that, and I'm putting it on the anti-static stuff here, such that all the pins here are flat up against the surface of the bench. Provide downward pressure back that end of the pins, and then let's see if I can do this more so you can see, and then just roll it a little bit, and now these legs are more at a right angle. I'm going to do the same thing on the other side. Okay, so now we'll take this 6850 and we'll see if we can get it in the hole here. Now again, these legs are in the socket, these legs are not. I'm going to lift and push back a little bit, and hopefully we can clear. Yep. Okay. Now we can press it down into the socket. Ta-da! So, that's great. Who's next? How about the 62256? So that is RAM, and I need light. 62256, so that's this one. And I apologize for the glare. 62256, and the notch is there. The U3 marking is there, so that's good. So we find the notch on the chip, which is there. And its pins are splayed, so we're going to go ahead and use our little straightening technique here to bring them in just a little bit. Lovely. Make sure our notches are properly oriented, and then you also want to make sure that the right pins are going in the right holes. You could be off by one pin in either direction or more, and that would be what's the word, bad. So don't do that. Alright, so one side in, the other side out. A little bit of a push and down. Down, down, down. And that looks pretty not too bad. Alright, so next is the 27C512, which is a giant EEPROM, and unfortunately it's taped over. So I'm guessing this is like a revision number or something for the software that's on this. But that's the EEPROM. So we're going to go ahead and grab that. We'll make sure our notches are pointing in the right direction. They appear to be. So we got a notch here and a notch here. Pins are splayed, so we'll go ahead and give this a little love. Okay. And one more. Okay. Make sure our notches are in the right orientation. And one side in, one side out. And, oh, I might have gotten it just right, because it appears that this is just going to drop right in. Perfect. And next we'll do the CPU, the Z80. That's this little baby right here. And again, notch is here. Notch. Okay. Pins are splayed, so this is the pins being splayed is usually indicative of factory fresh chips. And I don't know exactly why they're that way, but I'm sure it has something to do with the manufacturing process. So this side is all in the socket, this side is not. So we're going to push it back and down. There. Now, you might run into a little thing because these are dual wipe sockets, and what you have with the dual wipe socket is there's the edge of the plastic body of the socket, and then there's the edge of the metal wiper, right? So as your pins are coming down, they could hang up on the top of that metal wiper bit. So you want to be careful that you're actually getting past that lip. Both of those lips, the plastic body of the thing and the top of the wiper. So I think we're past the wiper body and into the thing. So I'm going to give this a little push. And the more pins that there are on one of these chips, the harder it is to actually push it into the socket. So, but I think we're in good shape here. So I'm just going to give it a little little bit more love. Make sure it's in there good. Make sure that's in there, good. All right, so now we've got our little bit of glue logic here. And we're going to do the one unique chip first. So that's the 74 HCT04, and that goes here. And I'm going to need the lamp again because I can't freaking see. 74 HCT04. Okay, so that is this one. And I'll just use my little pick to pull it out straight because we don't want to bend pins if we can help it. HCT04. Oh, we've already got a bent pin. That's awesome. My favorite. Wrong pliers. That would have been bad. I'm pretty sure I've got some HCT04s around here in my parts bin, but nevertheless, why risk it? Okay, so again, focus, you fool. It's not going to focus. I may have shut autofocus off on these cameras. I'm not sure. I'm going to have to double check that. And apologies for if focus is terrible. But splayed pins. So we're going to go ahead and address that. So a little bit of love and a little bit of love. Make sure our sockets or notches are properly oriented, and they are. 74 HCT04, that's what we're working with. So we're going to go ahead and put one side in. One side in. And then we're going to push it over sideways and down, and in it goes. Bam. All right. So now HCT34. 34? 32. Well, they're both identical anyway, so it doesn't really matter. Wow! There's a lot of bending going on here. It's almost as though Bending Rodriguez was here. Okay, so let's try and get these uniform-ish. So when the time comes to try and straighten them, we're getting a uniform result. Okay, so we'll do our little trick here to try and straighten these out. It's a little crummy, but we'll try and cope. And I'm selecting the socket that's... Oh, look at that. It may just go right in. It does. Hurrah. Okay, one more. We're running a little overtime, and I apologize for that. I said I'd be out of here by 11, and I'm not. So if anybody was depending on me being done at 11, well, I failed you, and I apologize. So these pins look a little more uniform than the last one, which is great. We'll give that a little bit of a thing. And drop that in. Yeah, so that one's going to need a little bit of lateral assistance. And then down. Lateral assistance and then down. Okay. I think we're in business. Cool. Now, an FTDI cable should be connected as shown. Yes, well, delightfully, as I mentioned at the top of this, I got the FTDI adapty thing, which is in this little anti-static bag. And ta-da! Now, ground is over there. So if I plug this little bugger right in there, RTS, RX, TX, CTS, GND. Okay, I don't know what that circle's about there. Okay. So, the other thing that this came with, and I think this is really handy, is a delightful USB to barrel jack cable. So, USB to barrel jack cable. So, if we're not powering it off FTDI, then we can power it off of there. 1000 mic. 100 mic. So this is weird. See here, and 100 microfarad capacitor. I didn't see any reference to that anywhere. $100 nanofarad, 22 picofarad. Those are the only caps. It doesn't list. I'm guessing that's just a power filter. And if you're running off of USB, there should be no variation. All right, so I need a USB, a micro USB Hoosie Flots. All right, tell you what, because I would really like to see this work. And I'd like you to see it work, darn it. All right. I'm gonna... bastard. I am going to do a thing. What am I gonna do? I don't know. I'm gonna see if I can get a micro USB cable real quick. Just a moment. I'll turn that so you can admire, if that is your interest. And I'm pretty sure I have a micro USB cable around here somewhere that'll work. Like that. Okay. I bought this as a charging cable, but I think it should also work as a data cable. Now, here's the trick. All right, so here's the trick. I don't want to plug this direct into my Pi 400 in the off chance that something goes wonky with the USB and it falls on its face. This has happened. It's a thing. So I'm going to plug it into my iMac, which has a USB hub. All right, so I'm going to plug it into my iMac, which has a USB. Excuse me, USB. Oh, come on, you. There we go. And I'll SSH in here so you can see it over there. Screen minus R minus D. Oh, that's not gonna work. Screen with 2 E's. Okay. Okay. So minus F minus A. So I'm just taking a look at the log on the iMac to see when it registers the USB serial doodad. Oh, come on. This is one of the pitfalls of working with such a small table. All right. Tasty USB cable. Oh, golly. All right. So, am I doing this wrong? I'm doing this wrong. The universal serial bus problem is, of course, is it upside down or right side up? Okay. So, USB ACM device, TTY ACM 0. Great. Now, first light. Here we go. Try and do bare cardboard here, just on the off chance that the conductivity of the anti-static mat messes everything up. Okay, shield eyes for blinding flash. Here we go. Well, we got a green light. Okay, so okay. Hi. So here's what I'm going to do. I am going to put that over there, and then after that is put over there, I'm going to come over here and I'm going to pop a terminal window and wonder where it went, and I'm sure it went on the other screen. It did. Okay. So that's good. I'm going to go ahead and do that and do that and use the correct keyboard. That's important. And maximize that, and then I'm gonna do that. Aha! All right. So I'm gonna do SSH. Okay. Hurrah! So let's do ls dev tty. Great. TTY star, even better. ACM 0. Okay. So which oh, what the hell is this thing called? Minicom. It's not installed. Of course it's not. Sudo apt-get install minicom. All right, so minicom. It's been a while. Let me accessories, text editor. Good. Well, if that's going to be in frame 2, then let's do something akin to that. And Untitled 1, that's good. So we want to say minicom oh, and this should help us, hopefully, with what we need to use for our com parameters. So 115, 208, and 1, right here. Well, right here. Okay, so actually, you know what? We don't have to go through all this craziness. We'll just go minicom. And actually, let's be root, just to be on the safe side. Okay, so minicom dev TTY ACM0. Oh man, minicom. There's a freaking config, right? Is it config? No init. It's setup. Okay. Minicom -s. Right. Oh. Minicom -s. Good. Okay, so serial port setup. We want to we want to say TTY ACM0. Then we want 115, 208, and 1. Great. Hardware flow control. Do they specify here? Okay. We'll use defaults. We'll try defaults for now. Okay, we'll try resetting. Ha! So memory top. 10, print, there's no place like home. 20, go to 10. List, run. Run. All right. So, built a computer. So what's next? The Raspberry Zero module. Definitely has some appeal, although I'm not averse to using a serial console. That's fine. But the CPM kit is probably going to be the next build. So keep an eye on the words are hard. Keep an eye on the Ribbit Nerding page if you're interested in seeing the CPM module build and test out and all that happiness. And yeah, I think this was good. So I need to do one little thing here, which is this. Yeah. So I want to thank everybody who watched for watching. I'll be, if you have any comments, you post some comments on this. That's cool. I'm happy to answer any questions if you have them, and even after the stream is over, obviously. But yeah, so we're here. We did it. We got the whole thing built. We got it turned on, first light. Ran a little basic program. So I'm pretty satisfied with that outcome. And I'm going to do some cleanup on it. I'm going to, wash the flux off and all that kind of thing. But it lit up, so I'm happy. Any questions? Put them in the comments for this stream. I'll keep an eye on that, and I guess that's it. So thanks for watching. Hope you have a great day, and don't do anything I wouldn't enjoy. Take it easy.